Okay, this is chapter 5.4, finding empirical probabilities. So empirical probabilities are based on observations of a real-life process and are calculated from the proportion of times an event occurs during that real-life process. For example, if I calculate the proportion of classes that you have attended so far this semester, let's say 95%, then this is the empirical probability that you will attend our next class. So what do we do if we need an empirical probability but we don't have the data to calculate it? Or the situation is too complex for us to find the empirical probability? The answer is to run a simulation. The key component of a simulation is that the randomness of the event needs to be represented by a random process with the same probability. So let's start with an example where we know the theoretical probability. This will give us something to compare our empirical probability to. Right, so for instance, what is the probability that a family planning to have 2 children will end up with 2 boys? So first part, we need the sample space. So what is the sample space for this random process? The hint is there are 4 outcomes in the sample space. So we've got one outcome where the couple has 2 children, both of which are boys. Another outcome where the oldest is a boy and the youngest is a girl. Another outcome where that's reversed. The girl is older and the boy is younger. And then the fourth outcome is that both are girls. So our sample space again has 4 outcomes. So in part B, how many of these outcomes have 2 boys? That's just one here. So just one outcome. And what is the probability that this family will have 2 boys? Well, since there are 4 outcomes in the sample space and one of them is both boys, then we've got a probability of 1/4 or 25%. So note that this answer in part C is our theoretical probability that a family with 2 children has 2 boys. So in a theoretical probability of 1/4, that's what comes from our sample space. Okay, number 4, the steps used to create a simulation to find an empirical probability are, first step is to identify the random action and the probability of successful outcome. So in our example, this is a single child. And then we're going to assume that the probability of a boy is 1/2 or 50%. Note that means the probability of a girl is also 1/2 or 50%. And number 2, determine how to simulate this random action. So we're going to use a random number table. You can use a random number generator as well. Even numbers 0, 2, 4, 6, and 8 are going to represent boys. Odd numbers 1, 3, 5, 7, and 9 are going to represent girls. Notice that 1/2 or 50% of the numbers are boys. And again, that also means that the other half or 50% of these numbers are girls. And so that mirrors what we have for the probability of a couple having a boy and a couple having a girl. Right, number 3, determine the event that you're interested in. The event we're interested in is getting 2 boys. Next thing, explain how you're going to simulate one trial. So we're going to read off 2 digits from the random number table. Each digit represents a single child. And so again, we're interested in a couple with 2 children, so that's why we need 2 digits, 1 digit per child. Next up, you're going to carry out a trial, record whether or not the event you're interested in occurred. And then the last 2, you're going to repeat the trial many times, usually at least 100 times, and count the number of times your event occurred. So this number of times the event occurred divided by the number of trials is going to give us an empirical probability. Okay, so since step 1 through 4 are done, we're going to move on to step 5 and run the simulation. Below is a partial copy of the random number table from the back of your textbook. So to get us started, we can close our eyes, point to a spot on the random number table. So for my example, when I did this, my finger landed on the second block of digits in line 7. So here's line 7. Went over to the second block, and that's where my finger landed. So starting with that 7. So the first 2 digits are 7 and 3. Notice these are both odd numbers, and we are using odd numbers to represent girls. So this gives a result of a family with 2 girls. We're going to use the total of 5 trials. We'll save the 100 or more trials for a computer simulation in the group activity. So we're not going to make you go to the random number table and do this 100 times. Right? And then we're going to continue using blocks of 2 digits in this line 7 to find the gender of the children in the next 4 trials. So we'll fill in our results in the table below. So again, notice those first 2 digits are for our first family. Again, both represented girls. So the number of boys, because we're interested in how many boys the couple has, is 0. And did the event occur? And the event is getting 2 boys or having both children be boys. And that did not occur. So we go back up to our table. Notice the next two digits are 1 and 1, which means that we get 2 girls again, so no boys, and we didn't see the event happen again. Next two digits, and keep in mind you can always close your eyes and put your finger down on the table again, but I'm going to keep reading from left to right. Next two digits are 7 and a 5, so again 2 odd digits, so both girls, no boys, and the event of interest, family having 2 boys, did not happen. Go back up, our next two digits are 7 and 9. These are both girls. Boys, number of boys was 0. And again, we didn't see a family with 2 boys in this case. And then our next two digits are a 5 and a 2. So girl on the first child, boy on the second child. So we got 1 boy, but we still didn't get a family with 2 children. So our event still did not occur. So how many times did the event of interest occur? There were 0 times. Our empirical estimate that a family with 2 children will have 2 boys at this point is that it happens 0% of the time, because it happens 0 out of the 5 times in our simulation. So is our empirical probability equal to the theoretical probability? If not, is it close to the theoretical probability? Remember that the theoretical probability, again from our sample space, was 1/4. And that is definitely not similar or close in size to 0/5. Keep in mind, we only did 5 trials in the simulation, so we're seeing something very different or fairly different from our theoretical probability. So again, our empirical probability is not very close to the theoretical probability in this case. And so last question down here at the bottom. If we run the simulation again, we'll do 5 new trials. Do you think we would find the same empirical probability? Explain why or why not. Probably won't. Keep in mind these are random numbers in the random number table, so we're going to have random outcomes, which means that results can potentially be different every time you run the simulation. So every time you pick a family of 2, get something different potentially, and every time you do a set of 5, you're going to get a potentially different empirical probability. Okay, so number 6, we're going to run the simulation one more time. So to get started, close your eyes, point to a spot on the random number table. And keep in mind you can press pause, try this on your own, or use our results here. So my finger landed on the second block of digits in line 4. So when I closed my eyes, put my finger down, I ended up here. So let's see, first 2 digits are 4 and 4. Both of these are even numbers and result in a family with 2 boys. So again, we're going to do this a total of 5 times, 5 trials, saving the 100 times or 100 trials for later. And we're going to continue using blocks of 2 digits in line 4 to find the gender of the children in the next 4 trials or next 4 families. And we'll fill in our results in the table as we go. So again, this 4, 4, those first 2 digits filled in the first column, both even, both represent boys. So we got 2 boys, and that meant the event of interest did occur. And that event, again, that we're looking for is that the couple ends up with 2 boys. All right, so continuing to the right, our next 2 digits are 7 and 1. Notice they're both odd, so they're both representing girls. So we got 0 boys, and our event did not happen. Next 2 digits are 6 and 0. So 2 even digits, so a family with 2 boys. So we got 2 boys, which means our event did happen. And I'm going to keep going to the right. Next 2 digits are 2 and 4. Both even, so we get 2 boys again, which means our event of interest did happen. And keep moving down to the right. Let's see, that brings us to the next 2 digits of 9 and 8. So we've got an odd number, which represents a girl, followed by an even number, which represents a boy. So we got 1 boy, but our event didn't happen because our event of interest again is 2 boys. So looking at this last row of the table, how many times did the event of interest occur? Got 1, 2, 3. So there were 3 times. So our empirical estimate that a family with 2 children will have 2 boys is 3 out of 5, or 60%. So again, this is an empirical estimate because it comes from our simulation. So is our empirical estimate, empirical probability equal to the theoretical probability? And if not, is it close? So our empirical probability, 60% or 3/5. And then again, remember that our theoretical probability, the one from the sample space, is 1/4 or 25%. So again, they're not all that similar in size. They're definitely not the same. I mean, it's somewhat subjective as to whether or not you think they're close in size. Okay, the law of large numbers, abbreviated as LLN, tells us that a well-designed simulation will produce empirical probabilities that get closer and closer to the theoretical probabilities the more trials we do. In other words, as the number of trials approaches infinity, the empirical probability should approach the true or theoretical probability. Right, so a number of trials. We only did 5 in our last 2 examples, because we weren't getting our empirical probabilities very close to the theoretical. If we increase this, then we'll see that they come very close, if not the same as the theoretical probability. So a few things that the law of large numbers does not tell you. Right? So for instance, in this first bullet, the first 4 children in a family are all boys. The 5th child does not have to be a girl. Right? It does not tell us that the 5th child has to be a girl. So keep in mind that a streak of boys, no matter how long, does not mean the next child is any more likely to be a girl. This probability is still 50% since the births are independent of each other. The law of large numbers also does not tell us that the order in which the boys and girls are born will be boy, girl, or girl, boy, girl, boy. We do expect half of the children to be boys, but the law of large numbers says nothing about the order in which the boys and girls appear. And the third thing, again, that the law of large numbers does not tell us is that every family will have half of their children be boys and half of their children be girls. We expect half of all the children to be boys, so all families all put together, but the law of large numbers says nothing about each individual family. So the larger the family, the more likely the family is to have half boys and half girls. Said a little bit differently, this last piece here, if you imagine a family with 2 children, it seems fairly reasonable to expect that you're going to see some that are all boys. But if you have a much larger family, let's say with 10 children, you're a little bit less likely to see all of them being boys, and you're going to get closer to half boys at that point. So keep in mind the law of large number only tells you that the empirical probability for the number of boys will be close to 50% after infinitely many trials. So again, not just after 5 trials, but a lot more. And on your next page, number 8, says the following graph shows what might happen after running a simulation to flip a fair coin 1,000 times and recording whether the coin lands heads. The graph plots the empirical probabilities versus the number of trials. So we're going to use this graph to answer the questions below it. And so again, keep in mind the empirical probabilities are over here on the left. This is on your vertical axes. So you go from about 40% up to 100%. And we're looking at whether the coin lands heads. So these are probability that the coin lands heads. And they're empirical probabilities because they're coming from the simulation. Number of trials is that how many times the fair coin was flipped. All right, so we can see that it was flipped 1,000 times. All right, first question, what's the empirical probability for a coin to land heads after 1 trial? So 1 trial, very first time it gets flipped, we had an empirical probability of 1 or 100%. 1 out of 1 time. First coin toss lands heads, we got 1 out of 1 being heads. Now it's empirical probability for a coin to land heads after 100 trials. So we got to 100 right about here. Let me switch colors. There's 100. Looks like maybe that happened around 54% of the time, or 54% of those tosses. So again, that's our empirical probability for a coin to land heads after 100 trials. So notice it's closer to the 50% than what we had after the first trial. So more trials, our empirical probabilities should get closer to the theoretical probabilities. So third bullet, does the empirical probability appear to fluctuate more at the beginning of the simulation or at the end of the simulation? So we go back up to our graph. Noticing that in this part of the graph, we see a lot of fluctuation. Drops down, it goes up, comes back down, goes up. But then afterwards, it starts to level out a little bit more. It's got some dips and valleys in here, but it does start to level out more towards the end. So if I exaggerate that here, I'm going to say that happens more at the beginning. I just draw another graph here. There's a lot of fluctuation in the beginning, and then it starts to level out at the end. Okay. All right, and last one, does the empirical probability appear to be settling down and approaching one particular value? And if so, what is this value? It does appear to be settling down. So on my exaggerated graph here, you can see that right here, it's leveling out. Go back up to our graph here from the actual simulation. This is where it appears to be leveling out. So it looks like that. Draw a straight line, so just a hair under 50%. So it's getting fairly close to 50%. Keep in mind, if we went out past 1,000 trials, we'd get even closer to 50%. So number 9, so how many trials do we need to do to ensure that an empirical probability is close to the theoretical probability? Well, it depends on how rare the event is. The more rare the event, the more trials that are needed. It's usually recommended that a simulation involve at least 100 trials. So note, even with 100 trials, there's no guarantee that the resulting empirical probability will be exactly equal to the theoretical probability. And in fact, if you keep in mind this idea of 100 trials, and look at what we got here from this graph, our 100 trials gave us an empirical probability that the coin lands heads 54% of the time. It's not exactly equal to the theoretical probability of 50%, but it's fairly close. Okay, so last piece here, number 10. The empirical probability does not equal the theoretical probability. There are two possibilities. The theoretical value is not correct. If possible, check the sample space in your theoretical probability. So that's the first possible explanation. The other explanation is that the empirical probability is just varying. Doing more trials will decrease this variability and get you closer to the theoretical probability. So again, the second option, if you think again of that graph we were just looking at, if your empirical probability is not the same as the theoretical one, you might be in the beginning of that graph where there's still a lot of fluctuation. And increasing your trials will get you out to that point where it starts to level out and approach the theoretical probability. So question then, how do you choose between these two possibilities? Well, this is one of the central questions in statistics. Are the data consistent with our expectations, or do they suggest that our expectations are wrong? So this is a question that we will continue to address in the remaining chapters. Right, so just as a quick example of what we mean by these two possibilities, imagine whether you want to test whether a coin is fair. And so again, your example here, let's say you want to test whether a coin is fair. So you decide to flip the coin 100 times. So you've got 100 trials, 100 coin tosses. Okay, and let's just say hypothetically you end up with 60 heads. So you get an empirical probability of 60 out of 100, or 60%. And so notice that doesn't match our expectations. A fair coin would have 50% for its probability of heads. So the theoretical probability ½ or 50%. So the question is this theoretical probability correct? Is the coin fair? Or is it just that our empirical estimate, our empirical probability isn't close because we haven't done enough trials? So we're trying to figure out maybe the coin is not fair, or do we need to flip the coin more times to decrease the variability? So this is again something that we'll look at in later chapters.